Okay, well, our first speaker today is Adrian Ioana, and he'll talk about existentially closedness and the structure of bimodules of II1 factors.
So let's see. Thank you, Bruce, for the introduction, and thanks to Brad and Elias for the invitation, and thanks to everyone for coming. So I'll be talking about existentially closeness and the structure of bimodules for II1 factors. This is some new connection between the notion of existential closed II1 factors and their bimodules. So I'll start. So this is joint work with my PhD student Hui Tan, who's graduating this year. So I will start by just telling you a little bit about the objects I'm considering. So very quickly, I'll mention what II1 factors are and what ultra powers are, because I'll need this to define existential closeness. So a II1 factor is just an infinite dimensional von Neumann algebra with trivial center and a trace. And we'll always equip M with the II norm defined by the trace. So for X, the II norm of X is just the square root of the trace of X star X. And also I'll define L2 of M to be the closure of M in the II norm. This is a Hilbert space, but more than that, it comes equipped with an M bimodule structure. M acts on L2 of M by left and right multiplication, and this is the so-called standard representation of M as bounded operators. All right, so some examples here. In fact, I think just the first two will show up in the talk, but of course, Murray von Neumann's hyperfinite II1 factor, the group von Neumann algebra L of gamma of any ICC countable group gamma, and then the group measure space von Neumann algebra L infinity of X cross gamma for, I guess I can use this, for any free ergodic probability measure preserving action. Yes. Oh, that's all right. Maybe I don't need to use it. All right, so these are II1 factors. And as I was saying, to define existential closeness, I'll use ultra powers. So what are these? So let me take a II1 factor M and U to be an ultra filter on a set I. So this is just a star homomorphism from unital star homomorphism from the algebra of the L infinity algebra on I. And then with this, I can consider the sister algebra of uniformly bounded functions from I to M. So this is this algebra. So this it's just functions X from I to M with the supremum of the norm of Xi being finite. And inside the sister algebra, we have a closed two-sided ideal of functions whose II norm goes to 0 along the ultra filter. So I'm looking at functions Xi such that the limit as I goes to U of the II norm of Xi is 0. So this is a norm closed two-sided ideal. So if you take the quotient, you'll typically get a sister algebra. But in this case, the quotient sister algebra, L infinity of I with values in M, mod J, turns out to be a von Neumann algebra. And since we started with a factor M, this quotient will also be a II1 factor, which is called the ultra power of M with respect to the ultra filter U. And as any II1 factor, it has a unique trace, which in this case is given by taking the lemming along the ultra filter of the traces of the components. Okay, so I did this in general. So now let's make it more specific. So from now on, all II1 factors, except ultra powers, will be taken separable. So all II1 factors will either be separable or will be of the form a separable II1 factor to the power U, an ultra power of a separable II1 factor. And also all ultra filters that I'll consider, unless I specify otherwise, U will denote a free ultra filter on the natural numbers. So a non-principal ultra filter on the naturals. Let's see. Okay. All right, so what are existentially close II1 factors? So these were first considered in a couple of papers by Goldbring, Hart, and Sinclair in 2012, and then by Farah, Goldbring, Hart, and Sherman in 2013. And the original definition is in terms of quantifier-free formulas, and it's a model theoretic definition. I'll give here an equivalent definition for separable to one factors, which is in terms of their ultra powers. And to give you the definition, let me just recall that if m is a two-one factor, then there's a natural embedding of m into its ultra power m to the u, where again u is a free ultra filter on the natural numbers. So this is given by sending x in m to the constant sequence equal to x in m to the u. This is the so-called diagonal embedding. This is a very important embedding for various reasons. Here, it will allow us to define existential closeness. So first, if m into n are separable to one factors, we say that m is existentially closed in n if there's a star homomorphism pi from n to the ultra power of m, whose restriction to m is exactly the diagonal embedding I.
Does this depend on the alpha?
No, I don't think it does. So, so in other words, any separable to one factor that contains m can already be realized as an intermediate subfactor between m and its ultra power. And a separable to one factor is called simply existentially closed, which is abbreviated as EC, if it is existentially closed in any separable to one factor that contains it. Okay, so in other words, you're existentially closed if any separable extension is already realized as an intermediate subfactor between m and m to the u. So from this point of view, so this is the operator algebraic definition. I think this is quite a striking property because everything, I mean, it's a striking property in either definition, but to me, this is quite powerful because anything that contains m already is in the ultra power. So, okay, so it's definitely a strong property, and I'll mention now some facts that were established in these two papers that I mentioned. So it's a strong property, but it's satisfied by many to-one factors. So any separable to-one factor is contained in a separable existentially close to-one factor. And because of this, there are continuum many non-isomorphic separable existentially close to-one factors. So there are continuum many non-isomorphic separable to-one factors, and within that, within the class of to-one factors, there's a continuum many that are EC. Also, the hyperfinite one factor is existentially closed if and only if the cone embedding problem has a positive answer. And I'll say a bit more about this later. And finally, being existentially closed has some consequences to the structure of the to-one factor. So any separable to-one factor that's existentially closed has to be McDuff. So it's isomorphic with its stabilization with the hyperfinite. So m is isomorphic to m tensor r. And also, just like the hyperfinite one factor has to only have approximately inner automorphisms. So any automorphism of m is a pointwise limit of inner automorphisms. All right, so this is what existentially closed to one factors will be for me, and this is some nice facts. So the main result of our work, or one of the main results, is a result about the bimodule structures of existentially close to one factors. So I'll spend some time telling you what I mean by bimodules and motivating the result that we give, but let me just stop and ask if there's any questions so far. Yeah. I believe that there's no explicit examples. Yeah, so the question was whether you can have an explicit example of an existentially close to one factor. There are no such explicit examples. So the only one would have been R if the cone embedding problem had a positive answer. All right, so as I was saying, our result is in terms of bimodules. So let me give you a little bit of an introduction to bimodules of II1 factors. So in 1980 or around then, Kohn realized that bimodules give you an approximate representation theory for II1 factors. If you're just, there was the earlier notion of modules over II1 factors. Well, the modules over II1 factor are just too, they do not retain much of the information about the II1 factor. Is really, if you look at just left modules, for instance, all you can recover is the dimension of the module. There's nothing else you can retain, but bimodules play the role of unitary representations for, say, countable discrete groups. So what is a bimodule? So let M be a II1 factor. So bimodule is a Hilbert space H together with a star homomorphism from the algebraic tensor of M and its opposite algebra to the bounded operators on H. So what this means is that I have two representations of M and M op on H which commute. And I'm assuming that the restriction of the star homomorphism to both M and its opposite are normal. And then the bimodular structure is simply given by applying this star homomorphism to a tensor and then applying it to your favorite vector. All right, so here's some examples. So the trivial bimodule L2 of M, which showed up earlier. So this has an M bimodular structure given by left and right multiplication of M. And more generally, if you have a II1 factor, let's say N, which contains M, L2 of N will be an N bimodule, therefore an M bimodule as well. And also a second very important example is the coarse bimodule, L2 of M tensor L2 of M. So here M acts by left multiplication on the first tensor and by right multiplication on the second tensor. This is quite different from the trivial bimodule. And maybe less obvious examples come from the L2 space of the Jones basic construction of M with any unital subalgebra, Van Neumann subalgebra P. And also the set B mod, so this is the notation that I'll use here. The set of all M bimodules is closed under taking direct sums and also under the Kohn tensor product. Yeah.
What's the bimodule structure in 3?
Sorry?
In 3, what's the bimodule structure?
So in 3, so here, sorry, I'm going the opposite way. So here, this is not a finite Van Neumann, this is a semi-finite Van Neumann algebra which still contains M. So when you complete it, the left multiplication of M on the basic construction still passes to an action on the Hilbert space. So it's still the action by left and right multiplication of M.
Kind of like 1,
except it's not finite, yeah. You have to complete the space with respect to the semi-finite race. And in fact, this is also, maybe I can write it. So this is an instance of the second example. So this is isomorphic as an M bimodule with L2 of M tensor, Kohn tensor product with L2 of M over P as M bimodules. No, it doesn't matter. It won't matter for my talk. Yeah, but it's, it's a bit of a sophisticated construction, but it has the naive properties that you'd want. So it really, I'll give only one line where I use some properties of the Kohn tensor product, but only very basic ones. All right, so what I'll care about is the fact that the set of bimodules comes equipped with two important, I guess, topology and weak containment. So there's the Feld topology and also the notion of weak containment, and these are connected. So I won't define what the Feld topology is, but I'll just tell you the one thing I care about here. So if I have two bimodules, two m bimodules H and K, the first one, H, belongs to the closure of the singleton K in the Feld topology, if and only if the following holds. So the following says, informally, that any matrix coefficients of H can be simulated to arbitrary accuracy in K. So if I pick any finite set S in M, any set of n vectors in H, and any epsilon, I can find some other n vectors in K such that the matrix coefficients, so here x, ci, y, dot cj, are within epsilon of the corresponding matrix coefficients with respect to eta 1 to eta n. And again, I want this for all x and y in the finite set S and for every I and j. I am defining what is enough. Yeah. Yeah, absolutely. Yeah. Now, there's the notion of weak containment, which at first looks a bit different. So the H is weakly contained in K if you look at, so again, we have to H and K, we have two star homomorphisms on the algebraic tensor product of M with M up, and H is weakly contained in K exactly when pi of H induces a smaller norm than pi of K on this algebraic tensor product. Okay, so this is very much analogous to the notion of weak containment for unitary representations. And it's equivalent, so H being weakly contained in K is equivalent with H belonging to the closure in the Feld topology of K tensor little L2. So what's K tensor little L2? This is just K tensor little L2 of Z, for instance. So this is an infinite direct sum of, a sum of infinitely many copies of K, which again carries an MM bimodule structure. So, but one thing you'll notice right away is that in particular, H being weakly contained in K is a weaker property than H belonging to the closure of K in the Feld topology. Okay, because obviously if I'm in the closure of K tensor little L2, I'll also be in the closure of K. And finally, H is weakly equivalent to K if H is weakly contained in K and K is weakly contained in H. And of course, this is the same as saying that these two norms are actually equal. All right, so these are some basic notions that I want to mention. And now, so again, I was saying that bimodules were first considered, I think, maybe first defined in the 80s, but already this fundamental theorem of Kohn on the classification of injective II1 factors can be stated in terms of bimodules. So Kohn's theorem says the following: so separable II1 factor is isomorphic to the hyperfinite II1 factor R if and only if the trivial bimodule L2 of M is weakly contained in the coarse bimodule L2 of M tensor L2 of M. Okay, so this is a complete analog of, well, I guess the definition of amenability, which says a group is amenable if and only if the trivial representation is weakly contained in the left regular representation. All right, so here's some additional facts about bimodules. So Popa, in his correspondences paper, noted that there is a minimal element with respect to weak containment, and this is the coarse bimodule. So the coarse bimodule L2 of M tensor L2 of M is weakly contained in any bimodule. And so there's a minimal element, but also you can see right away, or it takes an argument, but I don't think it's very difficult, that there's also a maximal element. So if M is a separable II1 factor, you can show that there exists a separable M bimodule, which I denoted by H max, and which is unique up to weak equivalence such that any other bimodule is weakly contained in H max. Okay, so you could definitely say, well, take the direct sum of all the bimodules, but this will turn out into something non-separable, but you can put a topology on the set of bimodules So that topology, I think, will be compact, so you can extract a separable maximal bimodule like this.
Can we be just naive and just take that and then use one of his forms here to decrement this sum of this file? That's the language. Oh.
Okay, so there's definitely a minimal bimodule, the coarse one, but there exists a maximal one. And now for the hyperfinite one factor, in fact, if I just start by assuming that the trivial bimodule is weakly contained in the coarse bimodule, then all m bimodules are equivalent, are weakly equivalent because of the following line. So if I take a bimodule H, this is isomorphic with its cotensor product with the trivial bimodule. This is somehow the analog of the algebraic fact that H tensor M over M absorbs M. And now cotensor product behaves well with respect to weak containment. So I'll have that this will be weakly contained in the tensor product of H with the coarse bimodule. But now M on the left only acts on the first copy, which will be absorbed into H. So yes, so we will get that the third bimodule is contained actually in an amplification of the coarse bimodule. Okay, so that tells you that any bimodule H is weakly contained in the coarse bimodule, but we also have the converse. So if you start by assuming that the trivial bimodule is weakly contained in the coarse, then actually all bimodules are weakly equivalent. And looking at this, Cohen's theorem says that at 1 factor m, a separable to 1 factor m is isomorphic to the hyperfinite 1 factor if and only if I can take the coarse bimodule as the maximal element with respect to weak containment. But of course, when m is the hyperfinite 1 factor, we just established that all m bimodules are weakly equivalent. So H max can be taken any bimodule, in particular the trivial one. But I should say that so H max exists, so there's a maximal element for any 1 factor m, but writing down an explicit bimodule that's maximal for a given 1 factor is usually non-trivial. And in fact, other than the hyperfinite 1 factor, some examples that I'll tell you, I'm not aware of any other example where you can say this is the maximal bimodule. I think that might be true for groups, yeah, already. Yeah. For groups, there might be some conjectures about.
For certain groups, it's like for finite completion.
Yes. So for the free groups, for instance, there is a quasi-regular representation which is maximal with respect to weak containment. I don't think it's explicit, but you know that there exists some subgroup of the free group such that the quasi-regular representation is maximal, but it's not explicit, as far as I know. All right, so okay, so our first result in particular will show that existentially close to 1 factors share this last property with of the hyperfinite 1 factor, meaning that for existentially close to 1 factors, the maximal bimodule can be taken to be the trivial one. Yeah.
Can you just give an example of a bimodule that cannot be written as in your examples? Is it as example 1 or something? Where it's just inclusion of it's a trivial bimodule or something.
Typically, this I don't see any reason why this would come from an inclusion of in a larger separable to 1 factor. But I don't have a result, right? But these don't look the same way. In fact, yeah. So this won't be of that form unless you have. So this bimodule has a p central vector, and yeah, if you can probably arrange for such bimodules to not be of that form. All right, so here's our results. So So I have several results, which I've labeled from starting with A. So our first result says, first consider the following 5 conditions, and I'm giving them separately so that I can explain them one by one. So the first one is that M is existentially closed. The second one is that any separable M by module H is contained in L2, in the L2 space of the ultra power of M. And again, I'm working with separable here. So there I have to, the reason I'm taking separable is because I'm taking a free ultra filter of natural numbers. So those are the first 2 conditions. And then I have 2 more. The third one is that any bimodule is contained in the closure of the trivial bimodule in the Feld topology. And 4 is that any bimodule is weakly contained in the trivial bimodule. Okay, and already from remarks that I made earlier, you know that that 3 implies 4. And finally, there's a 5th condition that's not in terms of bimodules, in terms of normal completely positive maps. So if phi is any normal completely positive map on M, then there is a sequence phi n of also normal completely positive maps such that phi n converges to phi pointwise in the 2 norms. So phi n of x minus phi of x goes to 0 in norm 2. And also each phi n has a very specific form. So each phi n is pretty much this, has the simplest form you can think of for a completely positive map. So it's a positive map of the form sum of ai x ai star. Okay, so 5, it's a rather surprising property. It says that any normal completely positive map can be approximated in the 2 norm by sums of completely positive maps of the form x goes to ax a star. All right, so the theorem says that 1 implies 2, which implies 3, which implies 4, and 4 is equivalent to 5. So in particular, if 1 holds, so if M is existentially closed, then conditions 4 and 5 hold. So in particular, any bimodule of any existentially closed 1 factor is contained in the trivial bimodule. So let me give you a quick definition then to sort of emphasize this. So let me take A to be the family of 2 factors which satisfy 4 and 5. So these are equivalent conditions. So it's a family of 2 factors such as any bimodule is weakly contained in the trivial bimodule. And we already saw that the hyperfinite 1 factor is contained in A. And this result gives you the first non-hyperfinite examples of 2 factors M which belong to A. And in fact, because we know that there are continue many non-isomorphic existentially close 2 factors, there will be continue many 2 factors in this class A. All right, so this is the statement of theorem A, and I'll take a few more slides to sort of emphasize various parts of this statement and also some open questions that come out of it. Let's see, are there any questions about this statement? So I'll repeat part of it a little later, but okay, if not, let me go ahead and forget about condition 5. So condition 5 was in terms of completely positive maps. So I'm going to focus on conditions 1 through 4. So again, the theorem in that case says that 1 implies 2 implies 3 implies 4, where 1 through 4 are as before. And let me just remind you that the 4th condition says that any M bimodule is weakly contained in the trivial one, which we define as M belonging to this class A. Yes?
The existence of a non-hyperfinite existentially closed factor, does it depend on the non-embedding problem?
No. No.
It always exists.
Yeah. All right, so the first question, since I have these implications, is whether conditions 1 through 4 are actually equivalent. Okay, especially condition 2 looks very much like existential closeness. It says something about, well, any M bimodule is contained in something having to do with the ultra power of M, which feels very close to existential closeness. So to tell you a bit more about this question, let me recall that a separable to one factor M has property gamma of Murray and von Neumann if when we look at the diagonal embedding of M into MU, this is not irreducible. So M prime intersecting with M to the U. So the relative commutant of M in M to the U is not the scalars. Or in other words, there are asymptotically central sequences in M that are not trivial, that are not asymptotically scalars. Yes? The coarse bimodule. Yes, the coarse bimodule is always contained in any, weakly contained in any bimodule. Yeah.
Item 2 looks somehow weaker than existentially closed because you have a II1 factor which is just locally universal.
Yes.
Ultra power contains everyone, which is kind of what 2 looks like. So.
Yeah, but that seems weaker than 2. Being locally universal, so locally universal means that the ultra power M to the U just contains any separable to one factor. I don't think that implies so. So it's also because I don't think property 2 passes to larger to one factors. So here's some properties of class A. So this is a proposition also with Hui. So these are some basic properties that are not too difficult to establish, but I think are kind of nice. So if a to-one factor M belongs to this class A, so again, any M bimodule is weakly contained in L2 of M, then so do M tensor R, the hyperfinite to-one factor, and any amplification M to the T of M. And also class A is closed under inductive limits, just like the class of existentially close to one factors. So if Mn belongs to A and Mn is contained in Mn plus 1 for every n, then the closure of the union of Mn's is also in A.
I'm sorry, what is class A? I didn't know.
Yeah, so class A is defined as those to-one factors with the property that L2 of M weakly contains any bimodule M, any bimodule H. All right, so 2 other remarks about class A. Yes, the hyperfinite one factor is in class A, and it's in fact the only explicit example that I know in class A. Sorry? They are not. I'm going to get to that, yeah. Yeah, you are absolutely right. So at least, yeah, one is stronger than the rest. Yeah. So condition C, so part C of this proposition says that if M is in A, but it doesn't have property gamma, then it must have property T. Okay, so what this tells you is that in this class A, there are no to-one factors that fail property gamma, but do not have property T. So for instance, the Frigru factors do not have property gamma and also do not have property T, so they're not in class A. And also, on the other hand, but I should say in part C, we do not know whether being in class A implies property gamma. However, part D says that if a to-one factor M satisfies condition 3, then it must have property gamma. And in fact, there's a very recent and a preprint posted by Amina Arachi last night or yesterday. This is it's very recent, yeah. So if M has property gamma, then conditions 2, 3, and 4 are equivalent. Okay, so the condition 2, 3, and 4 from this theorem are equivalent, if you assume property gamma. And this is nice because together with D, so our condition D says that if M satisfies 3, then it automatically has property gamma. So if it satisfies 2 or 3, it automatically has property gamma. So together with D, this tells you that 2 and 3 are equivalent for any separable to 1 factor M. Okay, so that means that in this theorem, we also have the implication from 3 to 2. However, we still don't know if there is a II1 factor M in A which has property T. And a negative answer to this is equivalent to 2, 3, and 4 being equivalent for every separable to 1 factor M. And I state it like that because I'm inclined to believe that there's no property T to 1 factor in class A, which would make conditions 2, 3, and 4 equivalent. Okay, but so to summarize this, this slide, this tells us that 2 is actually equivalent to 3, but whether 4 is also equivalent to 2 and 3, it's an open problem depending on whether there are property T to 1 factors in this class A. All right, so as Chris was saying, let me go back to the implication between 1 and 2. So this is the implication that if M is existentially closed, then any M bimodule is contained in the L2 space of the ultra power of M. And I should say, I just want to say a couple of words about the proof. So this is based on Shlachtenko's M's value semicircular systems. I won't define what these are, but very briefly, if you have a symmetric bimodule, so this is an M bimodule together with a involution that has certain properties, then you can always build a tracial von Neumann algebra, N, denoted like this. So it's gamma of M and H. So what is this? This is a tracial von Neumann algebra that contains M and has the property that as M bimodule, H is contained in L2 of N. Okay, so what this tells you is that really any M bimodule can be realized as a subbimodule of L2 of N, where N is a larger to 1 factor than M. That is not known. Yeah, and probably false, I would assume, but there's no way to prove that these constructions preserve commutability. So if we know that M is existentially closed, then of course I know that any extension N of M can be realized in the ultra power of M, and in particular L2 of N is a subbimodule of L2 of M to the U, but because H was inside L2 of N, I can now realize H inside of L2 of the ultra power of N. So once you have Shlachtenko's construction, the implication from 1 to 2 is not particularly difficult. All right, so what about the converse? So in the original version of our paper, we proved that the hyperfinite 1 factor satisfies condition 2. So we showed that any M bimodule is contained in the L2 space of the ultra power. And on the other hand, as you all know, I'm sure, there's this announced result of Jit, Natarajan, Vidic, Wright, and Yuan. So they announced a negative answer to the cone embedding problem, which implies that the hyperfinite 1 factor is not existentially closed, and which by this corollary B tells us that 2 does not imply 1. Okay, because the hyperfinite 1 factor satisfies 2, but is not existentially closed. So condition 1 is strictly stronger than condition 2. However, the following question is still open. So find a non-hyperfinite 1 factor which satisfies 2 but doesn't satisfy 1. So in other words, is there a separable to 1 factor which is not hyperfinite, which is not the hyperfinite 1 factor, and which is not existentially closed but satisfies this condition 2? That I also don't know. All right, so how much more time do I have?
Well, it runs till 10:30, but the date's in time for
Okay. I think hopefully I can finish before that. All right, so let me say a few words about the proof of corollary B. So I won't say how corollary B is implied, but let me mention sort of a result that is kind of independent interest that we prove in order to establish corollary B. And this has to do with Schlachthenkel's M-value semicircular systems. So start with two bimodules H and K. So if H is weakly contained in K for separable symmetric M bimodules H and K, then this implies something about the associated von Neumann algebras. So then there is a star homomorphism from the von Neumann algebra associated with the first bimodule to the ultra power of the von Neumann algebra associated with K tensor little L2. So this is the infinite amplification of K, which has the property that the restriction of pi to M is the diagonal embedding of M into the second ultra power. Okay, so what this tells you is that if you have weak containment bimodules, you get some sort of approximate embedding of the von Neumann algebra associated with the first bimodule into that of the second bimodule. After you really inflate your second bimodule infinitely many times. And just as a side note, this just seems to suggest a notion of EC triples, essentially called triples, where if you have a von Neumann algebra M which sits in both N and P, then sort of similar to the EC property, you can say that this triple is essentially closed if there is a star homomorphism from N to the ultra power of P, whose restriction to M is just the diagonal embedding. Okay, and this, if P is equal to M, this is just the fact that the inclusion of M into N is existentially closed. All right, so theorem C, so we prove theorem C in order to deduce corollary B, but in fact, there's other applications of it that I want to mention. So take any separable II1 factor M, and H to be a separable M bimodule, and P and Q to be the Neumann subalgebras. So first, we can show that bimodule H is weakly contained in the coarse bimodule if and only if it is actually contained in the bimodule on the right. So this is quite a mouthful, but it's you look at M inside M, it's free product with L of F infinity, and then you can take ultra powers of this, so you still have an embedding. And on the right, what I wrote there is really the L2 closure of the orthogonal complement of M to the U inside the larger algebra. Okay, so this tells you that you're weakly contained in the coarse bimodule if and only if you're actually contained in the specific, non-separable bimodule. And secondly, we also get a characterization of relative availability in the sense of Ozawa and Popa. So P is amenable relative to Q inside M. I won't recall the definition is in terms of the basic construction of M with respect to Q. But that happens if and only if there's an element, there's an X in the relative commutant of P and this larger algebra constructed as the amalgamated free product of M over Q with Q tensor on a billion von Neumann algebra to the ultra power, such that the projection onto M to the U is trivial, and then essentially X is a unitary, but the weaker condition that I just require that the projection onto M to the U of X star X has to be 1. Okay, so this is, if you've seen the definition of relative amenability, this is given in terms of bimodules. It basically says, so P is amenable relative to Q if the trivial p bimodule is weakly contained in the as a p bimodule in the L2 space of the basic construction of M with Q. So this is nice because it's an equivalent formulation of amenable relativity which doesn't depend on bimodule. It's really more dynamical in nature. All right. So let's see. So I got my last slides. So these are all about bimodules and existentially closed one factors. So I'll have one more slide on existential closeness for non-gamma one factors. So I remarked early in the lecture that any existentially closed one factor is McDuff. So in particular, it has property gamma. And let me just give you a very quick proof of that. So take M and embed it into N, which is M tensor 2x2 matrices. And if M is existentially closed, then we know that N can be realized in the ultra product. And therefore, the 2x2 matrices, which is the relative commutant of M inside N, can be embedded in the relative commutant of M into its ultra product. So in particular, the relative commutant of M into its ultra product is non-commutative, which is to say that M is McDuff, and in particular has property gamma. All right, so here's the question. So we know that one factors, existentially close to one factors necessarily have property gamma. So there's no existentially close to one factor without property gamma. But you can still ask, well, how close can a non-gamma to one factor be to being existentially closed? And I'm formulating this question in vague terms because I don't have a more precise, a very precise definition for it, but I can make it a little clearer what I mean by that. So let me denote by EM to be the set of all existentially closed extensions. Okay, so I'm looking at inclusions of M into larger one factors N, which are existentially closed, meaning again that N can be realized as an intermediate subfactor into the ultra power of M. And the question is, how large can this EM be? Again, this is still very vague. So a remark is in place here. So if you start with a non-gamma to one factor, there's quite a few restrictions on the existentially closed extensions that you can have. So let me take, M, let's assume that M is non-gamma, and let me take M into N to be an existentially closed extension. So then I have that M is contained into N, is contained in M to the U. And because M is non-gamma, I have that the relative commutant of M into M to the U is trivial. And with a little bit of work, you can show that in fact the relative commutant of M inside N to the U also has to be trivial. Okay, so if M doesn't have property gamma, then its relative commutant into the ultra power of any existentially closed extension has to be trivial. In particular, the relative commutant of M inside N has to be trivial. Okay, so any existentially closed extension of a non-gamma to one factor has to be irreducible. So a consequence of that is that M is not existentially closed in the following non-gamma extension. So take N to be M tensor L of Z. Here you can take any diffuse von Neumann algebra and do the free product with L of Z. So the free product ensures that you're non-gamma, and the first tensor product ensures that the relative commutant of M in N is non-trivial.
If you have elementary sum of the alpha power which includes N, then N is essentially called to that by definition.
Mm-hmm.
So there is no universal to one factor, but I would assume that somehow once we would prove that there are continuum, some optical elementary sum of those to the alpha power which equals N. It's not obvious, but that seems logical.
Sorry, so you.
Or it doesn't even have exactly. So that's just elementary. So let us take any subfactor inside the alpha power.
Mm-hmm. And then, sorry.
Well, then basically it embeds into ultra power because you picked it that way. So M is going to be existentially closed in any of those. And I would guess that one should be able to oh, okay, yes, but there are, I mean, the II1 factors that Taka constructed that cannot be embedded in same separable, they all are embeddable. So they're all going to be embeddable in the ultra power of M.
Oh, absolutely. So I completely.
So you have continuum many of them.
Oh, yeah. I didn't say how large can it be. Yeah.
Oh, you meant something else. I
mean something else. Yes. I don't mean in terms of cardinality. Absolutely. E to the M will always be, continuum many, will contain continuum many factors. Yeah. I completely agree. I mean more whether, can you say, something about this family? Can you have some general condition which guarantees that you're in E to the M? So in particular, okay, the reason I gave this example here is tells you that if you start with a non-gamma to one factor, there's a non-gamma extension in which M is not existentially closed. So E to EM cannot consist of all non-gamma extensions. So there isn't a to one factor M that is non-gamma and is existentially closed in the non-gamma universe, if you want. So that tells you that if you're looking at non-gamma to one factors, you have to be more restrictive in the types of existentially closed extensions you consider. So here's the result we prove. So there exists a non-gamma separable to one factor M, which is existentially closed in any extension M into N that is weakly coarse. So what does it mean to be weakly coarse? The orthogonal complement of L2 of M inside L2 of N is weakly contained in the coarse bimodule. So this is a general condition on a bimodule where you just say, L2 of N minus L2 of M is well contained, but even weakly contained in the coarse bimodule. And I should say that in some sense, this is the best you can do because of the following observation. So there exist non-gamma to one factors such that if you look at the orthogonal complement of L2 of M inside L2 of M to the U, this is weakly coarse. So maybe I can put it here. So the property that I'm looking at is that there are one factors M such that L2 of M to the U minus L2 of M is weakly contained in the coarse bimodule. So there are one factors M such that this is the case, but of course if I have that M is existentially closed into N, so I can realize N inside M to the U. Of course, L2 of N minus L2 of M will be a sub-bimodule here, so it will be weakly contained in the coarse bimodule. So in fact, so this tells you that there are non-gamma to one factors such that any existentially closed extension is weakly coarse. So you couldn't expect much better than in the theorem. And what are these non-gamma to one factors? This is also very recent. So independently in this preprint of Amin Marachi, and also in work in preparation by Ding and Peterson, it follows that this is the case if M is L of gamma, where gamma is any ICC countable group, which is bi-exact in the sense of Ozawa. So the class of bi-exact ICC groups includes all ICC hyperbolic groups such as the free group on at least two generators. So this is quite a large family that have this property. Of course, those are also not existentially closed, but yeah, they do have a very strong property. And I think I'll stop here. Thank you.